All right, thank you. Okay, guys, good morning. This is Acid Base 101, part 3, and this is about the pH scale and calculations. We're going to do part 3 in 2 parts. So part A is just describing what the pH scale is. And just as a reminder, we want to remember that water always has, or water or any aqueous substance, I should make that note here, has an equilibrium in place, always present, of 2 waters reacting to make hydronium and hydroxide. And the equilibrium constant for this is known as Kw, and that is equal to the concentration of the hydroxide times the concentration of the hydronium. And the other thing you want to remember is that if hydroxide concentration goes up by addition of sodium hydroxide or something like that, then the hydronium concentration goes down and vice versa. And we also want to remember that the value of Kw is 1 times 10 to the negative 14. So in a neutral solution, I spelled that wrong. In a neutral solution, the concentration of the hydroxide is equal to concentration of the hydronium, and that's going to be equal to 1 times 10 to the minus 7th molar. Okay, so what we use to measure acidity or basicity I don't know if I spelled that right, is called the pH scale. Okay, and the mathematical definition of pH is pH is equal to the negative log of the concentration of H3O plus in molarities. So this is a concentration in molarity. And that's moles per liter. Okay, so for instance, if we look at a neutral solution where the concentration of the hydronium and the hydroxide are the same at 1 times 10 to the negative 7, if we find the pH, so we would negative log the concentration of the hydronium, which is 1 times 10 to the minus 7, you negative log this comes out to be pH equal to 7. Okay, so any neutral solution, and the pH will be equal to 7. Okay, so that's just kind of a little introduction to how you calculate pH. And we want to talk about the pH scale. The pH scale in general goes from 0 to 14. So I'm going to draw a line here that represents the pH scale. In the middle-ish, I'm going to write the number 7. Over here, I'm going to write the number 0. And then up here, the number 14. And what we want to remember is that anything with pH between 0 and 6.99999 repeating, this is an acid. So this is where we have H3O plus concentration is greater than the hydroxide concentration. And anything with the pH of 7.00001 to 14 is considered a base, which is the chemical opposite of an acid. And so this would be where the concentration of the H3O plus is less than the concentration of the hydroxide. Okay, so just to give you some relative ideas about pH, these are very basic, very acidic, and this is very basic. Okay, and then it's 7 is neutral. So this is neutral is approximately what we can ingest. If I go down here, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14. It's approximately right. So 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13. So just to give you some idea, Down here, the pH, something that's very acidic would be like stomach acid. And then in the 2 to 3 to 4 range, this would be like pop or beer or wine, anything that's carbonated. And then in the 5 to 6 range, or 4 to 5, this would be coffee. And then neutral would be just pure water. Up here around the 8 to 9 range, this is like milk is a base. So sometimes you can drink milk and kill the acid in your stomach, right? Let's see what else. Okay, so up in the 10, 11 range, this would be bleach solution. And then up here is like hair remover. You guys have probably seen Nair or something like that. And then way up here is like oven cleaner. So that just kind of gives you an idea. Both of these ends of the pH scale can be very damaging to human skin. So anything that's down here can be very damaging, and anything up here can be very damaging. Excuse me. And our stomach has a special lining that can deal with those really low pHs. Okay, so what we want to remember, what are we gonna do? Okay, so we can also look at the concentration of the hydroxide by way of something called a POH. And that's just going to be the negative log of the concentration of the hydroxide. Okay, so we always want to remember that we know that the relative concentration of the hydroxide and hydronium, if one of them goes up, the other one goes down. Let's get this back up here. Sorry for my camera work. So we could know that if Kw equals 1 times 10 to the minus 14, and that's equal to the hydroxide concentration times the hydronium concentration. Oh my goodness, I'm going to rewrite that. The hydroxide times the hydronium. So 1 times 10 to the minus 14. Okay, and if we do a math function to this, we have a negative log of both sides. And here, then we get 14 is equal to the negative log of the concentration of the hydronium and the negative log of the concentration of the hydroxide. And so we can say that this would be, negative log of this would be POH, and the negative log of this would be pH. Okay, and remember that log of x times y is equal to log of x plus log of y. So that's how I got from multiplication to addition here. So we know that POH and pH, the sum of them will always be equal to 14. And if we know the pH or the POH, we can find the concentration of the hydronium or the hydroxide. So we know that if we want to go from the hydronium to pH, we take the negative log of the concentration of the hydronium. And if we want to go to the POH, we would take the negative log of the hydroxide concentration, and that would get us to POH. Sorry, my son. And then the sum of the two is always equal to 14. So if you know one, you can find the other. And if we want to go from pH to the hydronium concentration, we do 10 to the negative pH. That's the opposite of taking the negative log. And if we want to go from POH to OH concentration, we take 10 to the negative POH. And that's going to be equal to the concentration. Oops, these are concentrations of hydroxide and hydronium. Okay, so in part B, I will do several calculations with this relationship. Okay, thanks.